we'll look at questions on homework first. So which one did you have a question on? 20, 20, 23, and 26. So 20 is this one here. The set of all real numbers x such that x is not equal to 4. And I'll kick it down one just to hopefully help a little bit. 20. So we're wanting to graph this on a number line. So the first part of it, brace x bar, is saying the set of all real numbers. So every real number, but it tells us that x is not 4, yes? So our one key number that we have is 4, yes? Yep. And that'd be it. 23 and 24. 21, 23, and 26. So 21. So we're writing it in set builder notation. So we'd start off with this here. Brace x bar, the set of all real numbers x such that, well, what they told us is we have this here, yes? So we just need to rewrite this in as an inequality. So if I rewrite this as an inequality, we'd say 5 is less than or equal to x is less than yes, it's negative 5. Yep. Yeah. No, that's fine. I just, for some reason, overlooked the negative. You said 24? 23. So 23 will be similar, except instead of having just 1, 2, you just put the or. So instead of having one single statement, you would have 2 individual ones. Does that make sense?
So did I do this?
23. I would drop the negatives off x. So 23, x is less than or equal to 4, or x is, for 23, it would be not 8, but greater than or equal to. Yep, but that's it. Yeah, you had it. Yes, or so x is less than or equal to negative 4 or greater than or equal to 4 because it's going the other way. Now 26, we would start off the exact same because it's set builder notation. The set of all real numbers x such that 26, so it says the set of all real numbers greater than 19 and less than 32. So we're talking about between 19 and 32. So 19 is less than x is less than 32. Yes. Yes. All right. We're going to go on and get started with today's lesson. Yes, if you're finished with them, I'll take them. Okay. For the most part, if you haven't finished and don't have any questions on it, you can put them right on my desk. You can make a pile, and I'll take them that way. I don't have a specific tray. At the end of the hour, I do group them and put them together. Okay? If you don't feel comfortable with that, just hand it to me, and I'll organize it. So what we're looking at today, bless you, are parent functions and their transformations. Parent functions and transformations. Now there are four main parent functions that we're going to look at. Constant, linear, absolute value, and quadratic. Constant functions are, I think, one of the easier ones to pick out is we don't have a variable. When we talk about a function being constant, it is just a number. So like y is equal to 1, that is a constant function, or y equals 4, y equals 5, those are constant functions. And with constant functions, because probably going to get this tomorrow, question about this tomorrow out of the first 2 hours of the other 2 classes. This one here, if y is equals 4, it's just saying that it moved up 4. Or y equals negative 4, it moved down 5. Because it's just how did it change from 1? Moving it up, down. It's just a straight line going up or down. The other two that we have are linear, absolute value, and quadratic. And these are the parent functions right here. These are the graphs of them. And what we're going to be looking at today is how are they being changed? How are they being, there's going to be stretches, shrinks, up, down, left, right. We're going to be moving these and relating it back to these here, because for any other function of a linear, absolute value, or quadratic, we're really taking these graphs here that I just circled and moving them and stretching, shrinking, reflecting to get to the new one. And really that's what we'll be looking at today is how do we go from these graphs to those. And that's what we'll be looking at. Now, we won't get too much into the details of how it works for this one here, but what family does this fall into? How do we know it's absolute value? Right, because this here does have the absolute value bars, yes? What other way could we tell? The graph is a V, yes? All absolute value functions will have a V shape to them. Does it look exactly like the parent function? No. Do you all look exactly like your parents? No. I mean, there are some differences. Some of us favor one parent over the other, just genetics-wise, and how we look. But again, we look like our parents, one or the other, or both. That could be a good thing. That could be a bad thing. I'm going to let y'all decide that. But that's also why they call these, the first ones that we look at, the parent functions, because all other functions of them that we call transformations too, will look like those. Now this one here does have a vertical stretch of 2 and has moved up 1. There are transformations that apply to it. Now we'll get into that here in a minute. Because if I put the parent function back down, it would look something like this here. So they're not the exact same. There's been transformations applied to it. But we'll get into that here in a minute. Wrong way. What is this one's parent function? Linear. How do we know? Yep. Line. Linear. Linear functions are always going to be a line. Straight line. And the degree, so the x exponent that's attached to the variable will always be 1 when it's linear. And again, we can see that it's been flipped. It's going down instead of going up. It's not crossing the x-axis at 0 anymore. And it's not crossing the y-axis at 0, because the normal parent function for this here would have been this function here. That would be the parent function. It looks different, but it does have some similarities to it. Last one we're going to look at. This one here would be a, and we know it's a quadratic because, Yes. It has a U shape. Also, we have an exponent to 2. It's either going to be attached directly to x, the variable, or we're going to have the variable in a set of parentheses that's being squared. Any questions on this here so far? Now, the first transformation we're going to talk about is moving it up, down, left, or right. We're going to talk about a translation. I keep using that as transformation. I always flip them. And probably someone who is a stickler would probably comment on that, especially on the comments on the video if they saw it when I posted it or came across it. But again, so a translation is just up, down, left, right. A translation does not change shape, size, or orientation. It doesn't really mess with it. We're just literally moving it around the page. Now, for these here, I'm going to give you the general equations for these here. For linear, y is equal to a x plus k. And I'll move here in a second. Okay. Yep, sorry, I got that flipped for a second. I put quadratic under absolute value. Now, this here's the general form. This will be really the only time I write this out, because we could rewrite it again when we come across vertical stretch and shrink and reflection. But it's all referring back to this here. Each one of these, besides x and y, because those are referring to input-output for the overall function, have a specific meaning when we relate them to each function. So, up and down. If we're moving a function up or down, we're referring to, okay, what's being added outside of it. Does that make sense? So up and down is really going to be added outside of parentheses or absolute values. So if the number is positive, it's going to move up. If it's negative, it's going to move down. Left slash right is going to be with h. Now we can technically have a left-right movement with a linear function, but a lot of it is if we multiply through with the stretch and apply it, we'll end up getting the same place. So really, h is inside parentheses or absolute values. And it's always the opposite of what we think. Because what is the sign inside these parentheses or absolute values? Minus, yes? So if the value of h was negative, I'm going to open up a new slide. So if I said I had x minus negative 4, do we leave it as minus a negative? No, because what do? We change it to x plus 4. Well, here it's negative, so it would move to the what? Left, yes? 4 units. But how does it look here? Positive, doesn't it? So that's why I say it's the opposite of what we think, because we don't leave negative negatives. We change it to plus. So when we look at the function, it looks like it should be 4 units to the right, but it's actually 4 units to the, because the original function has a negative. And a lot of stuff with the or not a lot of stuff, when the translations talk about being inside parentheses or absolute values, it's always going to be the opposite of what we think. Always the opposite of what we think. So any questions on this so far? Now I know we haven't talked about A yet. We will get to A in a minute. Okay. This here is the first one that we're looking at. All right. So what is its parent function? Linear. Because we do have x, so it's not a constant, and it doesn't have an exponent or absolute value bar, so it's going to be linear. So the normal linear function, the parent function y equals x, yes? But what's different? We have what? -4. No. Yeah. So that's what's going to, our transformation that's affecting it. Now, so far, we've really gone over one. It's either going to move up or down, or it's going to move left or right. What do we think it's going to go? So left and right is where? It's our h, yes? And it was located where? Inside the parentheses, yes? Is the -4 or -4 inside the parentheses? No. So it's going to be up or down. So which direction do we think it's going to go? Down. How far? So it's going to move the whole function down 4. Now the reason that this is helpful, because if I know the parent function, is this right here. And the transformation is moving it down 4. So every spot on the graph would move down 4. So this would move down here. This would move 1, 2, 3, 4. And have an idea what the new graph looks like. And again, for the homework, I'm not going to make you graph these. All right? Really, this will probably be the only one we actually graph. But do we get an idea of how this works? Yes. And that's what the big thing with all these transformations, because we'll be doing more tomorrow. It's getting an idea of what is it doing to the function. How is the function working? How is it operating? Let's look at the next one here. What is its parent function? Yeah. It's an absolute value function. Now, we need to see where did it move, because the normal absolute value function just has the absolute value of x. But this one, we have +1 inside the absolute value bars, yes? Right, because inside absolute value bars are parentheses squared, it's moving left or right. And how far is it moving left or right? So it's moving one spot to the left or to the right. And the reason you say right is because, but inside parentheses, it's always the opposite of what we think. So it would be left. Yes, because again, inside the parentheses, for an absolute value function, we have y equals a parentheses x minus h plus k, yes? So let's get it back into this form, because really we're minusing whatever the h value is, yes? Well, the only way I can get that x minus, as we said, is if h is negative. Does a negative and a negative make a? So really, when we see x plus 1 inside those absolute value bars, really what we're looking at is x minus -1. That's really what it's supposed to be. Or we can just remember or think about it whenever it's plus, we're moving to the left. Whenever it's minus, we're moving to the right. Whenever we're inside parentheses or absolute value bars, it's the opposite of what we think. Opposite of what we think when we're inside absolute value bars or parentheses. Yes. Because for this here, a normal absolute value bar, absolute value equation is this. And at this point here, we're at the point 0, 0 for the parent function. Yes? Now, if I plug in 1, so you don't have to write this down. This is just kind of further explanation for why this works. Because if I did a t-table with our new function, x, y, we'll do -1, 0, and 1 to see how this works. With -1, we would have the absolute value of -1 plus 1. Yep, -1 plus 1 is, so this here is absolute value 0, 0, yes? -1, 0, wait. So where did 0, 0 move? Left to 1, yes? So at 0, do this again. Place the -1 with 0. 0 plus 1 is 1. Absolute value of 1 is still 1. So we have 0, 1. If we did it with 1, we'd have 1 plus 1 is 2. The absolute value of 2 is still 1, 2. I'll do one more with -2. -2 plus 1 is, absolute value of -1 is -2, 1. We can see the whole function move to the left. Even though it's plus, it still moves left. Does that kind of make sense? So it's a little weird in how that works, but it's just left 1. By the way, there's your answer. Any questions on up, down, left, right? Does that kind of make sense? A reflection. There's 2 ways that it can reflect. Yes. One is across the x-axis and one across the y-axis. It reflects across the x-axis when A is negative. When the A value is negative, it reflects across the x-axis. I'm just going to write this out because I can write this in words, but I have a feeling, because the first 2 hours I think they were probably a little confused, but I tried to put this in words. But whenever the sign in front of x, inside the parentheses, or inside the absolute values, we have that negative, then it's across the y. In some cases, I will denote this as b. So I'll just write it as, so y equals a, parentheses, b, x minus h squared plus k. Where that b is, that would be the reflection across the y. When that term is negative, then it will be across the y-axis. And the same thing is true with the absolute value, all right? But we're not going to deal too much with this value here. The only other place that this comes into play is with horizontal stretch and shrink. We can have vertical stretch and shrink and horizontal. But we don't focus too much on this here. Now, for those of you who do take college algebra, there's a chance they'll throw that in. So a lot of what we do in here will come to a certain point. College algebra just takes it a step further. That's the only real difference. So it makes sense here on when this flex across the y. Yes? Now, for the most part, this won't make a huge difference until we move it away from the origin for these here. Okay? Okay, so we'll look at the graph here. So if we want to reflect it across the x-axis, negative x squared. Well, it would help if I'm actually typing. Because if we have the negative out front, it reflects it across the x-axis. It's going straight down, yes? Now, we can go parentheses, negative x, close parentheses, exponent squared. Okay, it did give me 2 for that. Well, do y'all see a difference? You see the blue function? So when we reflect across the x or any axis, because we did this in geometry, I believe, because I remember if we got to it or not, it's the same distance from where we reflect the line. So what that's saying is that a point here, so we could say this point here is 0 or 1, 1, the y value is going to change. So it actually reflects it to this point here, and this point here is reflected to that one. It's reflected onto itself. So until that function's moved away from the x-axis, or, yep, come on over here. Yep, it's not going to do it. So, shift, parentheses, let's say shift plus 1, close parentheses. So we're talking about this function here that's moved 1 to the right. Parentheses, over 1, shift plus 1, shift. Now we can actually see where it's reflected across that y-axis, yes? So with the absolute value and quadratic, reflections across the y, without that movement left or right, reflect it right onto itself. It doesn't make a big difference. Does that make sense? Well, also anything times itself, negative times a negative is a. So just this parentheses negative x squared is actually just x squared. All right. So let's look at this one here. Okay, we're doing fine. So this one is a what type? Quad. Yep, its parent function is a quadratic. Now, this time we don't have anything added or subtracted inside parentheses or outside parentheses, yes? So it's not moving up, down, left, or right. But we do have the negative, yes? So it is a reflection across the, yes. And again, the negative is purely talking about reflection, nothing else, okay? Huh? So here, this value here is just saying it's negative 1. The 1 will tell us something more later. If there's a number instead of just negative, if it was negative 2, that would be telling us 2 different things. We'll cover that 2 here in a minute. Any questions on the reflection? How about this one? Linear. It is linear. Since we don't have an exponent, we don't have absolute value bars, it's linear. If it's just a number, it is constant. Okay? Yes. I reflected across the x-axis. Any questions on this here? How about this one here? It's linear, yes, and? So it's linear. Constant would be, I can write that up there, because y equals number. That's really all it's going to be. Or let me write it better than that. It's not so much number, it's going to be 1 plus k. Because really, if we're talking about linear function, it's only moving one direction, either up or down. It's not going anywhere else. So this one here is linear. So do we have a negative? No, we don't have a negative in front of the x, inside or outside of parentheses. So it's not a reflection. Do we have any addition or subtraction inside parentheses or absolute value? No, so it's not moving which direction? Left or right? It's up 3. Yep, up 3. So you ready for the next one? Quadratic, yes. Yes. How far? Yes. That's it. Questions on these here? We're ready for the next one. It would be absolute value. Yes. Yes. Or attached directly to the x inside the parentheses or absolute value. Inside parentheses or absolute value, it's across the y. If there's no parentheses or absolute value, it's considered to be outside, which would be the x. Questions on this here? This is the last one that we're going to look at. There is one other, which is horizontal stretch or shrink, but just like with left and right, it's the opposite of what we would think. So vertical stretch. And now it's considered to be a vertical stretch when A is greater than 1. I think this will make it a little bit clearer. When the absolute value of A is greater than 1. We do not care about the sign. We do not care about the sign of A. Because if this A is negative, what are we talking about? When it's negative, it's a, not that. What did we just do? It's a reflection. Because if A is negative, it's not talking about stretch or shrink. It's a reflection. The negative is purely with the reflection. Because it's a vertical stretch if A is greater than 1. The absolute value of A, the number itself, is greater than 1. It's a vertical shrink if 0 is less than A is less than 1. Or more technically, the absolute value of A is between 0 and 1. And the reason they add the absolute value is, again, to remove the negative case. Because, again, negative is purely with reflection. The A being negative is just telling us it's a reflection across the x. The number tells us if it's a stretch or a shrink. So if the number is greater than 1, not caring about the sign, then it's a stretch. If the number is between 0 and 1, then it's a shrink. So we can come back to this here. 3x. What's happening to the new graph? It's increasing faster. It's stretching along the y-axis. It's stretching vertically. So if it's shrinking, it means it's going to be wider. That's all it means. Okay? So this here, absolute value. Yes. Because the number in front of the absolute value is greater than 1. Now, we say this is a vertical stretch of, yeah, we're just saying how much did it stretch by? How much did it stretch based off its parent function? Because again, the basic quadratic that I showed you, the one in black, we're saying how much did it stretch by? A factor of 2. So all of them doubled. How about this one here? Quadratic. And it's a vertical shrink. Yes. What do we think? Are you ready for the next one? Yes? Because the number is greater than 1. And that 3 is in the place A. That's it. I won't write this out because I feel like y'all have got the hang of this, yes? So what would this one be? Absolute value function. Yes. Vertical shrink at 3/4. Because the number where A is supposed to be is 3/4. It's less than 1, so it's a shrink. I think that's pretty much the same one we did a minute ago. Yep, that was linear. So, well, we have it up here, so it is linear, and it would be a vertical stretch of 3. Yep. Yeah. Absolute value is the next one, yes. This one, not an absolute value. Quadratic, because we have the x squared. And then it would be? Yes. And this is part of the reason I threw it in, because saying that this is a shrink, I've had that many say that already today. And I threw this in here because of that, because we get very tempted because we have a fraction, it's going to be a shrink. No, we need to check and see what the fraction is. Because since it's 3/2, that's 1.5, so it is greater than 1. Just because there's a fraction or decimal does not guarantee it's a shrink. This is a stretch. This would be a vertical stretch of 3/2, or a vertical stretch of 1.5. Questions on this here? We have one more we're going to look at. I know it's not in the notes. But what's different about this function that we've been having, that's different here that all the others that we've had don't have? Because we do have a negative out front, yes? Well, so we have the 5, and we also have the -3, yes? How many translations or transformations do we have? 3. Because the negative out front is what, A? Across almost x-axis. Since it's outside, it would be x. Okay, that takes care of that. The +5 inside tells me what? It's going to be moving 5 units to the left, so left 5. Yes. So that takes care of this. And then what else do we have? Minus 3, which is going to be moving 3 units where? Because since it's outside, it's going up or? Is this any harder than what we just did? No, we're just taking each of the different components and putting them all to, and that's it. Questions on this here? And that is it. Now the first 3 are going to be combining sum. So the first 3 is going to be dealing with multiple transformations, not translations, because translations is just up, down, left, right. Now all of these here, you do not have to graph. Do not graph. Don't graph them. I'm not asking you to graph. So for the most part, the first 4 you're telling what the parent function is, describing the transformation. I believe the rest of them are just asking for transformations. Yep, and same with 9 through 15. So 9, 11, 13, 15. Because if it says odd, we're only doing odd. If it says even, you're only doing even for those set numbers. So you're doing 3 through 6, all of them. 9 through 15 odd, 19 through 25 odd, 27, 28, and 31. And that's it.
So 3 through 6, we can tell whether it's like quadratic, linear.
Because I think it says identify the parent function and family to which it belongs. Essentially describe the transformation. You don't have to graph it, but you're just describing the transformation. And they did provide the function itself, if you notice that there. So you're just describing the transformation. 9 through 17 describe the transformation, and it does say graph. You don't have to graph. You're just describing it. And the same thing